Hello students, welcome back to JCE Connect. We'll take one more design example, that is a simply supported beam 5 meter span carries a UDL of 40 kN per meter. In addition, the beam carries a central point load of 50 kN. The beam is laterally supported. Design the section and check the section for shear and deflection. Adopt limit state method of design. So in this particular problem, a simply supported beam is being given like this, and it is been subjecting both UDL as well as point load, that is concentrated load. UDL of magnitude 40 kN per meter is acting, and the point load is acting at the center as 50 kN. Okay, so this is the loading pattern for the beam, and it is simply supported, and the span is given as a 5 meter. Then here that small w is for a UDL 40 kN per meter is given, and the w, that is the point load, is given as 50 kN. Then the maximum bending moment, that is a combined effect of bending moment, or the combined bending moment, that is for the point load as well as for the UDL, that is WL square by 8 is for the UDL and WL by 4 is for the point load, and adding both we get 187.5 kN meter. This much is the bending moment. Then the maximum shear force, again for the combined effect, the maximum shear force, this is for the UDL, this much we get as a shear force, and for the point load W by 2. Then the total shear force what we get 125 kN. Then the next is you have to make it a factor, that is a maximum bending the factored moment what we get, you have to multiply it by 1.5, then we get as a 281.25 kN meter. Then the factored shear force calculate, then that is whatever the shear force is obtained here, you multiply it by 1.5, we get as a 187.5 kN. Then once we get my bending moment as well as the shear force, let us calculate the required plastic section modulus, that is a ZP. This is the required plastic section modulus, M divided by Fi into gamma MO. So M already calculated, substitute here. Then F divided by Fi into 10 to 6 into 1.1. We get this much as the plastic section modulus required, 1237.5 into 10 to 3 millimeter cube, which represent the strength of the section. And based on this section modulus, whatever the section modulus here calculated, based on this one, you have to choose the section. For that you have to refer IS 800 2007 page number 138. Try this section, that is ISMB 450. Then for that H is a 450 millimeter, width of the flange is 150, thickness of flange is 17.4, then thickness of web is 9.4 millimeter, and root radius is a 15 millimeter. Then the section modulus, that is elastic section modulus, as 1350.7 into 10 to 3 millimeter cube. Then the plastic section modulus 1533.6 into 10 to 3 millimeter cube. Then calculate next the depth of web as well as the for the flange width, that is the width of the flange, and that is required for the classification of the section. So here the depth of the web to be taken as H minus 2 times of TF plus R1, and this much we get as a depth of the web, as well as we have to note it down moment of inertia about ZZ axis, which is required for the deflection check. Then the next classification of section, calculate epsilon. Yeah, you know how to calculate the epsilon value. Then the ratio of flange to thickness of flange to thickness. This much we get, then which is less than 9.4, and hence it represents the plastic section. This element, flange element, represents the plastic section. Similarly, calculate the depth to thickness ratio for the web. Then we get as a 40.98, which is less than again 84, which represents the section is or the element is plastic, since both the element, that is a flange element as well as the web element, are plastic, hence the entire section is plastic section. And for the plastic section, the value of beta will be 1. Then the next is check for shear. Calculate the shear capacity of the section. We know the value of shear force actually acting, then the shear capacity of the chosen section, that is VD is into bracket Fi divided by root 3 into gamma MO, then the area of the section, which gives us 555 kilonewton. So take the 60% of that one, that 60% of that will be the 333 kilonewton, which is more than the actual shear acting, hence the chosen section is safe in shear. Next is design capacity of the section, that is the design capacity of the section in bending. So this is the formula to be used for the plastic section, and as well as it is of a low shear case. For the low shear case, this is the formula to be used, and substitute all the values. Beta is the 1, ZP for the section, and Fy all is substitute here, and we get finally as 349.95 into 26 Newton millimeter, which is more than the 281.25 into 6, and this 281.25 into 6 will be that is a moment, factored moment, which is more than the factored moment, hence the section is adequate. This section is safe in carrying the bending moment. Also, we have to do the check for deflection. Check for deflection you have to do for a permissible deflection span by 300. Then this much is the permissible. Then the actual deflection you need to calculate for both point load as well as for UDL. You have to calculate the deflection here. To calculate deflection at the center for both point load and UDL. So 5 by 384 into 10 into WL raised to 4 by EI is for the UDL. This gives the deflection for UDL, and this is the deflection for the point load. Add together, you add both, so we get the deflection 7.49 millimeter, which is less than the permissible deflection. Hence the chosen section is safe against the deflection. Hence we can write the deflection is within the permissible limit, hence the section is safe. Okay. So I hope you understood this problem. It's a simple problem. So only thing is you have to remember the formulas and how to calculate the different quantities step by step. Thank you.